So the relationship between y and x is that y is minus 1 over alpha times the logarithm of x. And x lies between 0 and 1. So a good way to start here would be just to refresh your memory about the graph of the... If we just graph the logarithm of x, it goes through 0 at 1. The logarithm of 1 is 0. And between 0 and 1, it's entirely negative. So what we're doing here is alpha is restricted to be positive. So minus 1 over alpha is a negative number. The logarithm of a number between 0 and 1 is always negative, and so y will always be positive. And at 1 it's going to be 0, and then it's going to increase up here like this. And the flatness of this curve will depend on the size of alpha. So we can see from this that the y values will be greater than or equal to 0. So the probability that y is below 0 is 0. Now let's just have a look at that in the setting that I suggested you do it in. So here I've got a graph of minus 1 over alpha, where alpha has been set to be 5 times the logarithm of x. It's graphed here. It goes up towards infinity at x equal to 0. Down here we have the PDF of x, which is uniform between 0 and 1. So you should have had a graph that looked something roughly like this. And what you have to do is to think, well, what is the output distribution of y likely to look like? Now we can actually observe a sample of size 10 on x by clicking on the step function here. And now we've got a set of 10 observations on x, and we can see what happens. So that's what's happening. X is uniform on 0, 1, so half the time it's bigger than a half. And let's look at what happens with these observations here. They come up and they hit the transformation, and the transformation has a very low gradient at that point. So even though these are spaced out, they're hitting a curve which is not increasing very much, and they all get concentrated into this space in here, creating a fairly high probability density in here. When you get down to here, these 3 points are hitting a curve which has got an increasing gradient, so they are spaced out more than the ones down here. For example, you could think about the median of x. The median for x is a half, because half the time it's bigger than a half and half the time it's less. If we come up here, we can see therefore that the median for y is just under 0.2. If x is a half or more, it hits this function and the value for y ends up being less than that value there. If the value for x is in this half of the distribution for x, then it comes up and it's going to hit the curve in this section. So half the probability for y will be concentrated in this small area here, and the other half will be stretched out between there and positive infinity, because the logarithm goes down to negative infinity, so minus 1 over alpha is going up to positive infinity, so there's no upper limit on the values for y. So that's just developing our intuition about this relationship. But let's think about how you would actually calculate the distribution for y. So we've got a uniform distribution for x along here. This is the density for x, and this is y equals minus 1 over alpha times the logarithm of x graphed here. A key observation to make is this. let's just think about a particular value for y. Let's fix y to be there. And if we're interested in the distribution for y, we can use the distribution function method, which says let's try to find the distribution function for y. Well, that's just the probability that the random variable y is less than or equal to y. So what is the probability that y is at that value or somewhere below? Well, because this function is monotonic decreasing, we can see that the value for y will be at that level or lower if x is in this region here. If x takes this value or higher, then the value for y will be that value of y there or less. And if we want to calculate that probability, well, we just have to take that region and calculate the area under the PDF over that region. And so what we've been able to do here is we've been able to take the distribution function for y, and we've been able to get an expression for it in terms of the distribution for x, which we know. So that's the idea of the distribution function method. So what I'd like you to do is to work through carefully through the detail of that, see if you can verify the required result, and then come back and we'll work through that in detail in the next video.